In Lesson 4.5, we're going to discuss some special types of applications of the multiplication rule in probability. We're going to look at conditional probability and then also how we can use complements to help us solve probability questions easier. A complement of the probability of at least one is something that we want to look at specifically in this section. So you'll be solving homework problems in this lesson 4.5 where you will see the phrase at least one used. And at least one by definition means one or more. So the complement in probability, remember, refers to the opposite of an event. And usually it means the negative. So the complement of getting at least one of an item of a particular type is that you would get no items of that type. So sometimes it's a lot simpler to work with the complement than it is to work with this compound probability of at least one. So in notation form, P of at least one is 1 minus the probability of getting none. So let's go ahead and look at our first example. This is example 1 on page 171. We want to find the probability of a couple having at least one girl among 3 children. Assume that boys and girls are equally likely and that the gender of a child is independent of any other child, meaning that gender is not influenced by previous births. So we're looking at the probability of a couple that has at least one girl among 3 children. So let's deal with the complement of this event first. So the complement of getting at least one girl is getting no girls. So that event would be a situation where they would have all boys. Now the reason why this is easier is because it's a lot more simple to solve for if we look at this compound event of having 3 boys. So the complement is boy and boy and boy. So the probability of getting a boy 3 times in a row, since we're using the word and, we're going to multiply those 3 separate probabilities. And since gender is equally likely, the probability of having a boy in each birth is 1/2. So we get the probability of a boy and a boy and a boy is equal to 1/2 times 1/2 times 1/2. And that equals 1/8. But remember, with these, you have to always look back at what you were originally solving for. We were originally finding the probability that they have at least This is example 2 found on page 172 in section 4.5. Here we are told to assume that the probability of a defective Firestone tire is 0.0003. If the retail outlet Car Stuff buys 100 Firestone tires, find the probability that they get at least one that is defective. If the probability is high enough, plans must be made to handle defective tires that would be returned by those consumers, should they make those plans. So we have a very low probability of having a defective tire. But this company is buying a large shipment of tires, so we want to know, is this going to increase the odds or the probability of having a lot of defective tires out of the 100? So let's go ahead and deal with the complement of the event. What's the complement of getting at least one defective tire? Well, that would be getting no defective tires. And so if we say we're getting no defective tires, then we would assume that all tires would work. So the complement of getting at least one defective tire is having all tires work. Now, since we're dealing with a shipment of 100 tires, then the complement would be that all 100 tires are good. So in verbal terms, that would be the first tire is good, and the second tire is good, and the third tire is good, and the fourth, and so on 100 times. So what do we do when we see the word and? Well, that's multiplication. And so we would have to multiply 100 times all of those probabilities. Well, what is the probability that a tire works? Is that 0.0003? Well, if you look at that sentence closely, 0.0003 is the probability that a tire is defective. So how do we find the probability that a tire works? Well, that would be the complement of that. So we just subtract 0.0003 from 1, and we find that the probability that a tire works is 0.9997. So then we have 0.9997 multiplied by 0.9997 100 times. Now we're going to look at some examples of conditional probabilities. In conditional probabilities, we will usually say, find the probability of something happening given that such and such is selected. So we'll see the phrase given that. So let's go ahead and look at how this is going to complicate the way. So here's an example we have a table showing senators, and these are Republicans, Democrats, and Independents, and then we also have the totals of males and females. So if we read across the top row, we have 46 male Republicans, and we have 39 male Democrats, and we have 1 male Independent. And then across the bottom row, we have 5 female Republicans, 9 female Democrats, and no female Independents. And here's our first question. If we randomly select one senator, what is the probability of getting a male, given that a Republican was selected? So there's a very subtle change here, and the subtle change is we see the phrase given that. After the word given that, or after that phrase, you need to really focus on who you are selecting. So it says we're selecting only Republicans. So what does that mean about the numbers that are given in the table? Do we get to use all of them? And the answer is no. Since it says we're only selecting a Republican, we have to completely ignore all of the Democrat numbers, the 39 and the 9, and we have to also completely ignore the independent numbers 1 and 0, because the Democrats and Independents have no chances of being selected if we are only selecting from the groups of Republicans. So you have to be really cautious when you set up your probability fraction, because you do not put the total. You don't add up all of the numbers together. So, what is the probability of getting a male given that a Republican was selected? So I'm going to phrase this as, what's the probability of getting a male Republican? So I want to only include the number of male Republicans on top, out of, and the total is what's really important, out of the total Republicans, not total people. So that would only be 51 Republicans. So 46 divided by 51 equals 0.902. Here we're going to look at the same chart, but answer a different conditional probability question. If we randomly select one senator, what is the probability of getting a Democrat or independent, given that a male was selected? So again, focus on that subtle phrase, given that, and what we see written after it is what we can only include in our total numbers. So what are we selecting? From the groups of males. So what do we have to completely ignore? Well, in the chart, if we're only selecting for males, we have to completely ignore the female numbers in that bottom row. So I would just cross that row out, and we only get to focus on the male Republicans, Democrats, and Independents. So that's what a conditional probability is. They give you the totals of everybody, but you have to closely read the phrase given that, and after that follows what you're selecting, and you have to ignore the other values. So since it says a male is selected, do not include any numbers of females in your probability totals. So what's the total males? Well, if we add the 46, 39, and 1, we get 86 total males. Now let's go back to the sentence that says we're selecting, or we're trying to find the probability of getting a Democrat or independent. Now when we do this, you have to also only look at the numbers of males for Democrats and the numbers of males for independents. So you have to completely cross out the female row for this entire problem. So or, what does or mean to do? Well, that means to add the separate probabilities. So I'm finding the probability of getting a male Democrat plus the probability of a male independent. So that would be 39 male Democrats out of 86 total males plus 1 male independent out of 86 total males. And if you add straight across, you have 40 out of 86. And then when you divide 40 by 86, we get 0.465. So again, after the phrase given that, focus on only those numbers for your totals and also for your numerators of your fractions.